All right, so we left off with this formula here, which tells us how to calculate the cumulative distribution function for a sum of continuous random variables. And it turns into this weird thing, this weird integral involving the PDF, so the probability density function for x, multiplied by the CDF for y, evaluated at some strange place. And this integral is taken over all possible x values. So what do we possibly do with this, right? That's really the question you should be asking yourself. And remember that the original question that we asked in the last video wasn't even, what is the formula for the CDF of the sum of x and y? It was, what is the formula for the PDF, the probability density function, as opposed to the cumulative distribution function. And remember how we move from CDFs down to PDFs, right? How do we get from one to the other? We mentioned this at the very end of last class. Well, we differentiate, right? So in order to get from the CDF for the sum of x and y down to the PDF, we just need to take a derivative. So what we know is that differentiating the left-hand side is, with respect to a, which is the variable, is going to give us the PDF. And what we have to do then is just differentiate the right-hand side. Right? So on the right-hand side, we would have the derivative with respect to a of this integral. We've got the PDF for x multiplied by the CDF for y, like that. Now, we do need to be, as always, right, every single time we do anything, pretty much, since this chapter has begun, I say the same thing. We have to be really careful here, right? So you might be tempted to look at this, and your gut reaction, which we've used a bunch of times in this course already, might be to say, I'm trying to take the derivative of an integral, so this is the fundamental theorem of calculus, and let me just roll along with that. That is not what this is. Right? We have to be extremely careful here. That's not what is being said here. This is not a fundamental theorem of calculus problem. Right? In particular, in order for this to be a fundamental theorem of calculus type of implementation, we would need that this integral should not go between two constants, but should instead have the variable a as something to do with one of its bounds, which it does not. Right? It's an integral taken over all possible x values. The integral, as far as the bounds are concerned, has nothing to do with the variable a. So this is not the fundamental theorem. What it is something that likely you probably have not seen before. What we need to do here, in order to say anything substantive about this, is to take this take this derivative, which is on the outside, and somehow say that it should be able to hop inside the integral. In other words, we would like to be able to say this. Right, so the integral is going to stay the same because the integral is with respect to x and the derivative is with respect to a. Now, in order for this derivative to come inside the integral, notice that once we integrate, all of the mentions of the variable x will be gone because we've integrated with respect to x and evaluated between two constants. So every single mention of the variable lowercase x will be gone. So this thing, this integral, really will only depend on the one variable that's left, which is a. Now, if we want to bring this derivative inside the integral, well, before we integrate this thing, it actually depends on the lowercase variable x and lowercase a, right? So this thing, the integrand, is a function of two variables, both x and a. So when we bring this derivative inside of the integral, it's not going to be a standard Calc 1 derivative d over dA, but it's instead going to be a partial derivative with respect to a of this function, which depends on two variables, both x and a. All right, so that's the first bit of subtlety. When we bring it inside the integral, it becomes a partial derivative. And what are we differentiating? Well, we're differentiating the entire integrand with respect to A. So the first thing I want to point out is that how do we even know that this can happen? And the answer is basically machinery that's outside the scope of this course, right? Essentially, our functions, right, our PDFs and our CDFs by association, that we're only ever going to consider PDFs and CDFs which are nice enough so that this will happen, right? And the one thing, as always, that we have to be careful of here is that this equal sign comes with an implicit caveat, which is that this is only going to be true where these derivatives exist, right? Which we've already seen come up a few times. So as long as this partial derivative is well defined, this procedure will actually work out, right? This is all valid as long as these derivatives exist. Now, why can we say that this equal sign is actually true, right? Why is this line equal to this line? Well, we've got this problem that these partial derivatives may not exist everywhere, and then we're trying to integrate these things. And so the caveat that we have to include here, which ends up being true for all the functions we care about in this course, the one thing we have to be careful of is that, sure, these partial derivatives may not exist everywhere, but where they don't exist, we'll have area 0, right? That's really the important part. Like in the example we saw on our homework, we found this CDF for that joint exponential distribution. And then when you take the double derivatives to get back down to the PDF, you run into entire rays, right? So the positive y-axis and the positive x-axis individually, where the second derivatives don't exist at all. But in the xy plane, the positive x-axis, or the positive x-axis and the positive y-axis account for 0 area. And so probabilistically, everything is still okay. All right, so that's the one thing, the one bit of subtlety you have to be aware of here. But again, all of our functions are going to work out in this course anyway, so that we don't really have to worry about this and we can use this freely. All right. Now, what actually happens now is that, let me just rephrase what we have. Right, we've got this line right here, and the idea, which I'm about to rewrite, is that this depends only on x, no mention of a, and so this can actually come outside of our partial derivative, because partial derivatives treat all the other variables like constants. This is a function only of x, this is a partial derivative with respect to a, so this whole thing in red can be treated like a constant and brought out in front. Right, so what we get here, just to rewrite what we had, starting from here, we've got that this is the integral from -∞ to infinity. Now, this comes outside of the derivative unchanged, like that. And now we're just taking the partial derivative with respect to a of f sub y of a minus x, right? So this is what we're left with. Now, again, partial derivative, because there are, at least in theory, there are two variables that are independent of one another here. Independent as calculus variables, of course. Not a probabilistic notion there. And what we're saying here is that we're trying to take the partial derivative of a function of basically another function, right? This is really just the chain rule, right? So we take the derivative of a minus x with respect to a. That's just going to be 1 minus 0, since we treat x like a constant with respect to a. And so we're just going to get 1 for the derivative of the inside, and then we have to take the derivative of capital F sub y. And we've already used the fact that CDFs differentiate down to PDFs. So this derivative simply turns out to be the derivative of the inside, which is 1, with respect to a, would be 1, times the derivative of capital F sub y, and that is exactly the PDF for y, lowercase f. And the chain rule says to keep the evaluation at the same place. So we do that. Right? In other words, what we've got here is we've got the integral from -∞ to infinity, the PDF of the variable x evaluated at x, multiplied by the PDF for the variable y, evaluated at this strange place a minus x, and the dx just tags along for the ride. So we have this here, and this is, to make the convolution notion explicit, this is exactly the convolution of fx and fy. All right, so this is what we would call, the notation would be fx, and then we use the star to indicate a convolution, fy, and the evaluation here is at the variable a. All right, and this is a symmetric notion. It doesn't matter which order you do it in. That's an exercise in the book. And we would read this, right, the way you read this here. This is fx convolved with fy evaluated at a. All right, so the long and short of it is that if you want to figure out the PDF for a sum of two random variables, it's the same as figuring out the convolution of their individual PDFs. And the only thing we used to get here was that these two variables had to be independent. All right, so as long as you've got a sum of two independent variables, notice we didn't have to assume identically distributed or anything like that, just independence. So if we've got two independent variables, we add them together, we can figure out the PDF for that just by convolving the individual PDFs for x and y together. And that's the main idea. We'll do some examples of this in the next class.